2.6 and E-text activity. And so whenever to design the following girders, okay? So this is our floor plan here, or the framing plan. And so whenever we look at this, we can see that our beam spacing is 6 feet and 8 inches. And so we're going to be using that information to calculate out our tributary width here for these beams. These are the exterior beams here, up here at the top, and then these are interior beams here, okay? So let's go ahead and let's scroll down here. We also see this criteria here. And so we know that the dead load is going to be equal to 50 PSF. So remember, we can take this dead load, multiply it by our tributary width, and that'll end up giving us the uniform beam loading. Same thing for here, the floor live load. This 100 PSF comes from IBC table 1607. It's used for hotels. We've got this FY value of 50 kips per square inch, or 50,000 pounds per square inch. We're going to have a plaster ceiling, so we're going to be using that for the deflection limits and the dead load. Perfect. Create this load diagram here too. So 18 is going to come from both the live load, converting that to decimal form, which is just 8 divided by 12 which per feet. And then whenever we go to calculate out the live load, you'll remember based off of IBC table 1607.1, for a hotel, live load will be 100 square feet, or pounds per square feet. We're going to multiply that by our tributary width as well, which is going to be 6.67 feet. Once again, dimensional analysis, we're going to be left with the pounds per foot. And whenever we multiply this outright, we're going to end up with 660. This would actually be 666.6 is what we can call it. So that's pounds per feet. And so then in terms of our total uniformly distributed load, so we could put down this total is going to be equal to that dead load plus the live load. It's just important to remember this because we're going to end up using this calculation for the deflection limits here. But with this total, we're going to end up with 1,000 pounds per feet is what we're going to end up calling that, because this would be 0.9, but as this decimal goes out forever, it's pretty much going to be 1,000. So now we can end up creating that load diagram here, which is this pounds per feet. And remember, this is for an interior beam, so we're doing interior beams here first. So now that we've got this, we can go ahead and let's just unbox these answers here. We'll unbox this, and then let's also box in this answer too. So now we've got that. So let's go back here. So create a beam diagram, we just did that. Calculate end reactions and maximum moment. And so this is where you could end up throwing this particular situation into MD solids. It could do those calculations for you. However, we're going to go ahead and actually do that ourselves here because we can end up using the equation sheet. And so what we're going to end up doing is we're going to bring out equation sheet. Please do remember this scenario right here in our equation sheet is scenario 2. And so the reaction moments here, RA equals RB, because this is a symmetric load. RA and RB are actually going to be the same. As this equation is WL divided by 2. And so now what we can end up doing is we can plug in our values. It's basically 1,000 pounds per feet multiplied by 18 feet, right? Divide that by 2. What we're going to end up seeing is that those units are going to cancel. This is basically 1,000 times 9, right? 18 divided by 2. So we've got 9,000 pounds. So that's going to be the end support reaction. That is also going to be our maximum shear as well. So I'm going to go ahead and take note of this. V max is what that's going to be, the max shear. So now let's go ahead and let's continue with 1D. So 1D, they're asking us calculate that maximum moment. So we're going to go ahead and do that. So max moment, just as we can see right here on our equation sheet for scenario 2, M max, that is equation 12.5, is going to be WL squared divided by 8. And this max moment is going to be occurring at the center of our beam. So we can go ahead and put this information in here. 18 squared divided by 8. And remember, these units we're going to end up with pounds times feet for our final unit because this length is now being squared. This is pounds per feet. And so now what we're going to end up with is 1,000 multiplied by 18 squared. Then we're going to divide that by 8. That'll end up giving us 40,500 pounds times feet. And so this is our max moment. Now remember, Vmax, also the same thing as VA, this is going to be the same case here. This is our max moment, right? So M max, this is also going to be equal to MA as well. Okay, so that's what we're writing out there. Because in the second, you will remember that MN, let's plug in our values here. MN is greater than or equal to 40,500 pounds times feet multiplied by that 1.67. And so now what we're going to find out is that MN must be greater than or equal to 67,635 pounds times feet. Now remember, this is just to ensure that we are also taking into consideration the safety factor. Basically, we're going to be 167% of this value here, of that applied load that we end up finding. So that's what we're going to end up with for MN there. And so now let's go ahead and let's get ready to continue. And so now they're going to ask us in this next one, calculate the required plastic section modulus. And so as you'll remember, that value is going to be ZX. And so whenever we go in here, this is 1F here, right? So MN is equal to Fy multiplied by ZX. Okay, we know that value. MN, we also know what that must be greater than or equal to. And so now what we can end up doing is, because this is equal to MN, we can basically plug Fy times ZX in right here, right? So we can end up doing something like this: Fy ZX greater than or equal to 67,635 pounds times feet. And so now on this, if we end up dividing by Fy, we divide it on here, we divide on this side, we can end up determining here that ZX must be greater than or equal to the 67,635 pounds per feet divided by Fy. Now, what was Fy? If you'll remember, we go right here, it is 50,000 pounds per square inch. So pounds per square inch. And so if we end up going through here and we calculate this out, we've got 67,635 pounds times feet here for our unit up here on the top. And so what we're going to actually need to do is convert that to pounds times inches so that we can end up having all of our units in the same. We don't want to have feet and also inches, and I'm going to explain why that is the case here shortly. But we're going to go ahead and put this 1 foot 12 inches. That's our conversion factor. Now feet are going to cancel, feet are going to cancel. Going to be left with inches there on top. We're going to divide this by that 50,000 pounds per square inch. And then what we're going to end up saying is that this pound is going to cancel with this pound. Now, this is basically 1 divided by 1 divided by inches squared, right? Now, that's the same thing as just having inch squared on the top, just like here. I'll put it over here, inch squared. That's going to end up being where it's just inches squared, right? Since we already have this inches up here, it's going to be basically multiplied by that. And so ZX must be greater than or equal to, it's going to be a value that's going to be in inches cubed here. And what we're going to end up finding is that it's 16.2 is what we end up getting for that value there. And so now, based off of this, we need a plastic section modulus that's going to be greater than or equal to 16.2. And so if we end up going to our steel request website, you remember you can end up clicking right here on the wide flange steel beams. Sometimes it's a little weird where you have to click this twice. Appears at 4.4. And so now that does exceed the required 16.2. And so what we're going to go ahead and do is we're going to try, I'm going to go ahead and write this down, try W12 by 14. Now I'm going to make note ZX is equal to 17.4 inches cubed, and the IX value, which is the moment of IX, is also equal to 88.6. Remember, that is inches to the 4th power for that unit there. Other things that we're also going to want to mention is that web thickness, and so that's going to be 0.2 inches, and the depth is going to be at 11.91 inches. And so if we go back over here, you can end up 1 for D and then 0.2 for required nominal moment, as well as the plastic section module. We chose an efficient steel wide flange to carry the load, but now what we've got to do is we've got to check the shear capacity. And so this was F, and then this was G. So I'm going to put 1G down right there. And then what I'm going to go ahead and do is I'm going to get a new piece of paper here, and we're going to go ahead and continue with 1H here. So now we want to check that shear capacity. So shear capacity doing is we're going to end up using this equation here. Vn must be greater than or equal to Va multiplied by that shear safety factor. And now in this case, just as we said before, right? We said whenever we were calculating out those support loads, the actual max shear is going to be at that point of this load, right? Where we are applying that support load. Then, since this is a horizontal line, basically our shear diagram is going to be a sloped line downwards, and so it's never going to be as big in the positives as whenever it's first on this support reaction here. So VA is going to be equal to, in this case, Vn greater than or equal to Va. That was at 9,000 pounds is what we ended up finding. Now for the entirety of this course, we are also going to end up using 1.5 for our shear safety factor unless otherwise specified. And so now what we end up finding whenever we calculate this out is that Vn must be greater than or equal to 13,500 pounds. Okay, so shear strength, the nominal shear strength must be greater than or equal to 13,500 pounds. Now, as you'll remember, Vn is also equal to 0.6 Fy and then multiplied by D times Tw. What we can do now, since we know these values, right, that's what we had just written down previously here, we can end up plugging this in. So Vn is going to be equal to 0.6 multiplied by 50,000. So Fy in this case was that, what was that, the 50,000? Yeah, 50,000 pounds per inch squared. Then we're going to multiply this by a unit of inches here, right, for the depth, unit of inches for the thickness. And so what that's going to end up being is D is 11.91 inches, and then our thickness is 0.2 inches. Now what ends up happening, this inch and this inch cancels with the square inches down here, right? So now we're going to be left with a unit of pounds, which tells us, hey, that's good. So whenever we calculate this out, what we're going to end up getting for this value is actually 71,460 pounds. Now, this value is greater than or equal to this value, right? So that's a good sign. This is going to end up working this 12 by 16 beam in terms of that shear. Now, the next thing that we've got to do is actually calculate out those deflection limits. Okay, so we've got 1I now. That's what we're going to end up doing. So we got to find the deflection limits is what we're going to end up doing here. Now, this is a plaster ceiling, and so just like we were saying in our notes, we've got to end up calculating out the max or the deflection limit for the dead load plus the live load. Then we've also got to calculate out the deflection limit for the live load, just the live load itself. And so now what we can end up doing is we can end up using this equation here. Now the deflection must be less than for a plaster ceiling. In our slide, we end up saying the dead load plus the live load must be less than or equal to whatever L is divided by 240. Keep in mind, this L value does need to be in inches because deflection always calculated in inches. Then this value is going to be L divided by 360 as well. All right, so now what we can end up doing is we can end up plugging these values in. So we got that 18 feet because that is our beam span. We can take that 12 inches divided by 1 foot. We're going to divide that by 240. So now feet going to cancel. We're going to be left with a value of inches. What we're going to end up finding, and this is actually the same as our example from yesterday in class, is that the dead load plus the live load, the deflection cannot exceed 0.9 inches. For our live load, whenever we calculate this out, it's going to be 18 feet. Once again, multiply by 12 inches, divide that by 1 feet, get those units to cancel, so we're left with inches, divide that by 360 here. What we're going to end up finding for this one is that it was that 0.6. So This is 0.6 inches. And so now based off of this beam that we end up choosing, and we apply the dead load and live load onto that beam, it cannot deflect in the center by more than 0.9 inches, meaning it cannot sag down more than 0.9 inches. Same thing here for just the live load. Whenever we just put in the live load in there, we calculate the deflection or the amount that the beam's gonna sag. It cannot exceed 0.6 either, okay? So now what we're gonna end up doing is we're going to move on to 1J, and that's going to be where we're going to calculate out the actual deflection. So we're going to check the actual deflection using the beam formula. Now, if necessary, we're going to end up revising our member choice. We're going to have to choose a new one potentially if the deflection exceeds either of these values for each particular scenario. So now for 1J, let's go ahead and let's go in here. If we look at our equation sheet, you'll see that this scenario, right, that we have here is scenario 2. Now for the deflection, max deflection, for this, it is the case where it is equal to this value. Max equals 5 times whatever the uniform distributed load is to the 4th, and then we're going to divide that by 384 multiplied by E multiplied by I. Now I is the moment of inertia, right? E is the modulus of elasticity, also known as Young's modulus. And then W is our uniformly distributed load. For each of these cases, we're going to end up first calculating out the dead load plus the live load, and then afterwards we're going to end up calculating out the deflection just for the live load. So L also is just the length of that beam. Remember, we got to convert all of these to have units of inches, by the way, so that we're remaining consistent with our units. So we're going to take 5 times now. If it's the dead load plus the live load, remember, the dead load plus the live load, that was equal to 1,000. And so now that's 1,000 pounds per foot. And so what we can end up doing is we can convert this. We want pounds per inch. Now, if I want to cancel with a feet down here, I got to put a feet up here, and then I'm going to have inches down here. Now 1 foot, there are 12 inches in 1 foot. So we can end up doing that. Now feet are going to cancel with feet. We're in pounds per inch, so that's all good. Now in terms of L, that's the length of that beam. We said that it was 18 feet. Now what I can do is I can multiply this by a fraction. We're going to put feet down here, inches up here. In 1 foot, there are 12 inches. Feet are going to cancel. We're going to be left with inches here. This is raised to the 4th power. We're going to divide this by 384 multiplied by 29 times 10 to the 6th power. That's what E is, the modulus of elasticity for steel. Remember, that is based off of the material that you're using. And so for all of these, it's going to end up being steel, unless otherwise specified. And then for our I value for this, you'll remember that we wrote that down right over here. The I value for the 12 by 14 beam was 88.6. And now what is the unit for that? That is going to be inches to the 4th power there. Okay, so now what we can do is we can calculate all of this out. We can plug all this into our calculator. And what we are going to end up determining here is that this is going to actually be equal to 0.92. Now, here's my question for you all. 0.92 inches. Does that exceed our deflection limit? It does by 0.02 inches. Because it exceeds that, even though it's only exceeding it by 200ths of an inch, it is no good. So what we've got to do is we've actually got to revise. So we've got to revise the beam member selection. Now, we had chosen a 12 by 14 last. What I'm going to end up suggesting now, and I'm going to cross this guy out, is I'm going to try a W12 by 16. Okay, so that's what we're going to end up trying out. Let's look up some of this, the properties of a 12 by 16, and hopefully this will, in terms of, let's see, our properties. Let's go ahead and write this down. 12 by 14, we're going to scroll down. 12 by 14, we went 12 by 16. And so now, what we should end up having here is ZX, the plastic section modulus. We see that that is 20.1, which is better. X is here. So IX, let's see here. IX is equal to 103. So 103 inches to the 4th power. Okay. And so now, as you can see, the IX value is greater than the 12 by 14, right, which was just 88.6. So whenever we put this into our actual formula, since this is on the bottom here, it should make this value smaller. So let's go ahead and let's try this out. Since we know already that this was equal to 0.2, what we can actually do is we can set up a fraction here so that we can calculate out dead load plus live load just like this. If we end up saying that this is 0.92 inches, right? What we can end up doing is, so we have 0.92, we can actually multiply this by 88.6 inches to the fourth divided by 103 inches to the fourth, right? And this is going to actually scale that for us just based off of using this I value. It's going to basically cancel those out. And so what we're going to end up finding is that this is going to be equal to 0.79 inches, right? Which is less than the 0.9 inches, which is the max deflection. So that gives a check mark, right? If you're getting thrown off by this, basically this is just a different approach. You could end up taking your 103, plug it back into there, and exchange it for the 88.6. You are going to end up getting the 0.79, but this is just scaling it down, right, based off of using 103 instead of 88.6. So now the next thing that we've got to do is we've got to check the live load deflection. So this is just the deflection whenever the live load is being applied. Now the live load, you'll remember, was, 666.6. What I'm going to go ahead and do just for safety is I'm going to actually round that up to 667. So we're going to take this 384 times E times I. We're going to go 5 times. Now, as we said, here's that value, right, for the live load. What I'm going to end up doing is I'm going to round that up, 667 pounds per foot. And we're going to multiply this by, we need to get this into inches, right, because we're calculating out deflection. I'm going to put feet up here. I'm going to put inches down here. Now in 1 foot, there are 12 inches. Feet and feet going to cancel. We need to multiply this by the length of our beam. Length of our beam, once again, was 18 feet. So 18 feet. We're going to end up multiplying that by a fraction. Feet need to be on the bottom, inches on top. 1 foot, there are 12 inches. This is to the 4th power. We're going to divide this by 384. Multiplied by E. Now E in this case is the same, 29 times 10 to the 6th. That is pounds per inch cubed. And we're going to go ahead and multiply this out by the moment of inertia of our beam, which is going to be that 103, since we're using the 12 by 16 inches to the 4th power. And what we're going to end up finding is that this is going to be equal to 0.52 inches. Now for the live load, we need to have a deflection that is going to be less than or equal to 0.6. So that value is less than or equal to 0.6. And so that also ends up getting the check mark of approval. Now, my apologies, because I think that we do want to actually not have this equal, so we just want to make sure that it's less than that. So I'm just going to end up taking out those. So we're going to keep that just less than. I'm going to scratch that as well. Okay, so the W12 by 16, in terms of this deflection, it passes the test because our ZX value was greater than the 12 by 14. It's also going to pass our other tests as well. Looks like Adobe efficient to carry bending moment and shear. So what you could end up doing is you could end up recalculating all of these values, but the final design is going to be the 12 by 16. What I also suggest is actually putting this into MD solids using a 12 by 16 beam, apply that load, and then actually showing the analysis of everything in there. But 12 by 16, that's going to be the beam that we want to end up choosing, and this is going to be 1K. All right, so this is for the interior beam for the 2nd floor. Hope that was helpful. In the next video, I'm going to end up showing you the exterior beam calculation, which is going to be very similar to this process.